Okay, good day, good people. Let us look at the compound bars. Okay, this would be your compound bars. It is the combination of two uh, different materials connected in parallel. I've chosen parallel so as to explain certain things. We've already dealt with the series on chapter 1, stress and strain. We dealt with the series connection. Now, hence, chapter 2, they don't repeat the series connection. They only repeat it when we are dealing with the change of material or the deformation of material as a result of transference of energy, heat. Okay, now this would be your compound bar. You are having two different types of material that are having two different strength of material, young modulus. Okay, and the force that is being applied, it is the force total here, and the force total will affect the steel and the copper. But before I continue with this, please make note we are having different types of parallel connection. This is one of them. Then you are having another one of which it consists of your concrete, but the principles are the same. You deal with it the same. Okay, let's say this is your concrete, then there's a reinforcement steels. Okay, this it is as well parallel connection. How you deal with it, it's exactly the same as how you deal with this parallel connection. Then you are having this one, which rods are being connected to your bar there on top or hanged on the rope. You are having something like this. Okay. Steel. Let's say this is steel, this is copper, this is steel. It is still parallel connection. How you deal with it, it's exactly the same as how you will deal with that one. But when coming to this one, if this force it's not at the center, it is somewhere there. How you are going to calculate this force applied or the forces acting on this beam, you will then use the equilibrium principle. What are the equilibrium principle? It is sum of the clockwise forces equals to sum of the anti-clockwise forces. When you are dealing with this type of a parallel connection and this force, it is not at the center, it is somewhere there, and they would want you to calculate the distance from here to there or the distance from here to there. How you will calculate that distance and the force, then you will apply, more especially the distance, then you will apply this principle here of equilibrium principle. Okay, then you are having another connection. You are having a pipe, whether it is hollow, right? Then inside that pipe you are having another steel pipe there. It is still the parallel connection. How you work it out, you will deal with it the same as that one. Okay, now let's look at the principles. But this one of a concrete and the reinforcement, when you deal with this one, you are having the area total of that block, you are having that area total, and you are having the area of the reinforcement steel, then you are having this portion as your area, this portion as your area. Now, for you to be able to get this portion, you must obviously get it from minusing this from there, then you will get that portion of a concrete there. You will get it, okay? That's how you work with it. In getting this one, area concrete, it will be area total minus the area of the reinforcement steel. And if you are having four of them, that means it will be multiplied by 4 here, isn't it? Then you get the area of that concrete. Then you can use this area concrete and the area steel to calculate the stresses in that parallel connection. Okay, now let's look at the parallel connection. The parallel connection simply says the length of a copper, it is the same as the length of your steel. Then the change in length here, it will be the same because the force applied, it is the force total. The force which is applied here, it is the force total. Okay. Now the force applied, it is the force total. Let's say the force which it's been applied there, it is 100 kilonewtons. The force which it's applied here, it is 100 kilonewtons. It is the total force which is affecting the steel and the copper. And we are told that under parallel connection, the change would be the same. Meaning, if the force it's been applied, force tensile, the steel will elongate and the copper as well, it will elongate. But look at how they are elongating. They are moving away from, as a result of the applied force. It means the stress under this steel, it is the stress tensile. Then the stress under this copper, it is the stress tensile. Looking at this scenario, because they are pulling, there's that force pulling away from the object. Okay, now copper, it is of a soft material, then steel, it is of hard material. Under this 100%, you will realize that maybe copper will assume maybe 30 kilonewtons. Maybe as they are applying 100 kilonewton, then copper start to bend when the force it is at 80 kilonewton. It means the young modulus of copper, it is there. This indicates the toughness of that copper. Then copper, it will start to bend there. At what force? 30 kilonewton. It means that which is left, it is what? It is 70 kilonewton. Then as they are pulling at that 70, then steel starts to do what? To bend. There. The whole region here, it is the young modulus of what? Of steel. This is how you must view your parallel connection. How copper will absorb the applied force. It is not the same as what? As a steel, because this one, it is of soft material, the other one, it is hard. This one, it will break quicker comparing to that one, as I've indicated in this diagram there. Now, change in steel, it is change in copper. They will change the same. Steel will become the benchmark. Steel will become the benchmark. Copper will not extend beyond the level of what? Of steel. That means steel, it becomes the benchmark. Hence, the change in length, it is the same. Now, when coming to the force applied, as I've explained, that under this 100 kilonewton which it's been applied, force total 100 kilonewton that it is being applied. The force steel, let's say it will absorb 30 kilonewton, then the force copper, it will absorb what? 30 kilonewton. When you add what's on the right hand side, it must be equal what you have on the left hand side. Now, this is how you will deal with your parallel connection. Under your parallel connection, you need to make note. The change, the length, it is the same. The change in length would be the same, but when coming to the force, because of the different types of material, how those material are going to absorb the applied force, it is not the same. The soft material will break up quicker comparing to the hard material. That's why we are using this formula. That's why we are using this formula based on that explanation. That's why we are using that formula. Again, I want you to look at your formulas in this manner. Here, we are dealing with them from the force perspective. You can as well deal with those formulas from the stress perspective. Now, let's start with the change in length. What is change in length? It is force multiplied by length over area multiplied by Young modulus. Now, what do we have here? What do we have here? Force over area is a stress. That means you'll have stress multiplied by length over Young modulus. That means your change would be this formula as well. Now let's look at the force part of it. How do we calculate stress? Stress, it is force over area. Now force would be stress multiplied by area. Now these two formulas, they are applicable. These two formulas, they are applicable. You can substitute this with from on your x-axis, or you can work from the force perspective. If you don't want to work from the stress perspective, it's fine. You can always calculate the whole stresses that they are looking for from the force perspective, meaning you will get the force of copper. Then from the force of copper, then you can calculate the stress. Then it will be stress force copper over area copper, and stress steel, it will be force steel over area steel. Then you get the stresses. Whether you work it out from the force perspective or from the stress perspective, it doesn't matter. Your answer will be the same and the correct one. Okay, hopefully with this given example, I will be able to deal with them in those both in those perspective. Okay, hopefully I'll be able to apply them in those both perspectives that I've just explained. Now let's wipe so as to do the application of the given principles. Okay, what's happening now with my gadgets? Okay, I'm trying to wipe. What's happening now? Oh my goodness. Okay, let's wait some few minutes. Okay. Where's my eye cursor? I don't see my eye cursor now. Oh my goodness. Where's my eye cursor? Okay, there it is. Let's wipe. Okay. Okay, let's look at the given question there and apply. Let's look at the given question there and do what and do the application. Okay. Let's take the blue pen. Okay, it's working. Okay. Now, from the given statement, a brass pipe with outside diameter. Now, please, that which will help is for you to interpret the given statement in a form of what? Of graph, so as to know what's given and what needs to be calculated. We are given a brass pipe. This is a brass pipe. It's the outer diameter. Okay. The outer diameter, it is given D brass. It is given as 45 mil. Okay. And inside diameter, then we are having the inside diameter. The inside diameter, the D in of that brass, it is given as what? As 35 mil. Okay, is placed concentrically over a round steel bar rod. Now, there's a round steel bar inside. There's a round steel bar inside. Okay, it's a solid one. This one, it is hollow. Then there's that solid one inside there. Okay, and the diameter of that solid one, the D in, it is 32 mil. Okay, that's what we have. Then the length of this, it is given as 420 millimeters. Okay, okay, ridge plates are fitted to the ends. Okay, there's plates fitted to the end. There's plates. Okay, determine the stress induced in the rod and the pipe due to the load. Now we are given the force total. It is 60 kilonewton. Then we are given the Young modulus of steel. It is 200 gigapascal. Then we are given the Young modulus of brass. It is 100 gigapascal. Yes, now they want us to calculate the stresses. Now, what is it that we know? We know under the parallel connection. We know under the parallel connection, firstly, that length steel equals to length brass. That we know. Okay. Then we are having the change in steel equals to the change in brass. Now, we will then use that formula. Stress steel equals to length steel over E steel equals to stress brass multiplied by length brass over E brass. The length and the length will cancel out, since when we said this, it is the same. It then means under the change here, it then means under the change, don't forget, how did we get that change? We got the change from brass, it is force L over AE. We said it that this, it is stress, force over area. Hence we are having stress L over E. That's how we got it. Okay. Then we are having okay, there's my eye cursor. Okay, there it is. Then we are having stress steel over E. Steel equals to stress brass over. Then we can then make any of the stresses the subject of the formula. If we are making the stress steel the subject of the formula, then we will be having Young modulus steel multiplied by stress brass over Young modulus brass. This will make it our first equation. That's what we have. That's what we have. Okay, that is the first part. Remember, the first equation, it is stress steel equals to stress brass multiplied by Young modulus steel over Young modulus brass. Then that's your first equation. Okay, then we come to force total. We are given the force total equals to force steel plus force brass. Okay, like we said that force would be the stress multiplied by area. If we are taking the root of the stresses, then this is the root that we'll be taking. Now I'm having stress steel multiplied by area steel plus stress brass multiplied by area brass. Now this would be your second equation. Okay. Now we then have to calculate our stress, our areas based on the given information. Okay. Based on the given information, we then have to calculate our areas. In calculating the area of steel, it will be pi multiplied by 0.032 squared divided by 4. Then you get your area. As I calculated, my area is 8,0425 or 423 times 10 to the power negative 4 squared. Then in calculating the area of a brass, since well it's a hollow, it will be pi open bracket big D minus small d squared close bracket divided by 4. Then it is pi. The big D, it is, remember the big D is given as 0,045 squared minus the inner diameter, it is 0,035 squared close bracket divided by 4. Then I got my area as 6,283. I took it to the fourth digit multiplied by 10 to the power negative 4 squared. Now, I've managed then to calculate my areas. Okay, I can then substitute my areas into this. I can then substitute my area into formula number 2. Okay, now let's go to the new page. Okay, stress steel, it is stress brass multiplied by the brass. Okay, did I make the okay, can I make brass the subject of the formula, because I've worked it out using the brass. Now if I use the steel, then I have to stress brass equals to stress steel multiplied by Young modulus brass, of which it is 100, divide by Young modulus steel, of which it is 200. The 100 and the 100 will cancel out. Then you will have 0.5 stress steel. Remember, that's your equation 1. This is what we have here. Okay. Then we come. Force total, it is 60 times 10 to the power 3 equals to stress steel multiply by the area steel. Our area steel, it is 8,0425 423 times 10 to the power negative 4, right, plus stress plus multiply by the area, it is 6,2832 times 10 to the power negative 4. That's what we have there. We can then, from there, you can then say substitute stress B into second equation. Now, where we have stress B on the second equation, where we have stress B in the second equation, then we will be putting what? That. We will put that, okay? Now, we will be putting that. Now, we are having 60 multiplied by 10 to the power 3 equals to stress steel multiplied by 8,048 0423 multiplied by 10 to the power negative 4 plus, where there's B we put 0.5 stress steel multiplied by 6,2832 times 10 to the power negative 6. That's what we have there. Okay, that's what we have there. Then we get our answer in multiplying and adding the two. I got my answer as, I've already worked it out. Please work it out as well. I got my answer as 1,11,839 times 10 to the power negative 3 stress steel 60 times 10 to the power 3. Therefore, stress steel would be 60 times 10 to the power 3 divided by 1,11839 times 10 to the power negative 3. Then I got my stress steel as 53,64 megapascal. Then you are going to say substitute this answer that you got into first equation in calculating what? The stress B. The stress B would be 0.5 multiplied by the answer that we got there, 53, is it 53,64. Then we get our stress B because it is half of that. Then I got my stress as 26,824 megapascal. Now this is how you apply. This is how you apply the first part of your compound bar. The material expanding as a result of what? Of the applied force. This is how you apply it, good people. Then I will send the second video dealing with the expansion as a result of what? Of transference of energy, heat, so as to give you the principles that you need to know regarding that. Thank you, good people.